if they were here, there is a parallel session. Okay. So, yeah, for those that weren't here before, my name is Andrea Aime. I work for GeoSolutions. And in this presentation, I'm going to talk about mapping beyond the web Mercator using GeoServer. GeoSolutions is a small and medium enterprise established in 2006. We do many things related to GeoServer, in particular much of the raster work that goes on into GeoServer, but we are active in other parts as well. And for example, I'm the maintainer of the rendering subsystem, which also involves vector data, of course. And yeah, in this talk, I want to show you what GeoServer can do besides just doing tiles, which is what most of the people are talking about today. So it's really a presentation about projections and the act of reprojecting data. So why use Web Mercator? Web Mercator is that projection that Google Maps and OpenStreetMap and Bing and many others use. So why are there reasons to use it? Well, it's everywhere, it's free. There's a lot of freely available base map out there in this map projection. Think OpenStreetMap, think of OpenMap tiles. There's Google, Bing, MapQuest, and so on. So there's a lot of choice and often no financial commitment in using these tiles as a base layer. But the moment you use it as a base layer, you have to use it for everything else. Anyways, there's a lot of choice. What's not to like? Why use this map projection? Because it's familiar due to how popular these services are, OpenStreetMap and Google and so on. This is how the people are used to see the world, which is a tragedy, really. This projection is horrible when looking at the entire planet. And I mean, I'm going to talk about it later in more detail, but look at how big Antarctica is, and even Greenland is ginormous there. It's not that big. Then finally, why? Because it's easy. There are tons of interesting map projections around, but why do you have to learn all that and to manage the reprojection and to understand the characteristics of each projection, when to use which one and so on, when you can just get away with one? For many people, it's just so easy to get there that they don't even think about it. Finally, and one nice thing to say about the Web Mercator projection, it's fair to the dateline. The dateline is sort of the end of the world when it comes to longitude, latitude data. And many maps projections are breaking the maps at that point. This one doesn't. It's one of the few that doesn't. So you can wrap around your map and have a sort of a continuous spanning without ever hitting a border of the map. And I can tell you, if you live in New Zealand, you gotta love this feature of this projection, because they live very close to the dateline. So I gave you some reason why people use it. Let me give you some reasons to avoid it instead. One reason to rule them all is the distortion. Earth is a geoid, which is close to an ellipsoid, which you can think as a sphere if you want to simplify it to the extreme. Have you ever tried to take a football and cut it and make it flat? I can assure you, you cannot do it without distorting it. You have to flatten it with force because it's a double curvature surface. A single curvature surface, like a cylinder, you can cut, unfold, and it's flat, no problem. A double curvature surface, there's no way to make it flat without distorting it. So you have to accept distortion in some way. There are distortions that we want to minimize and others that we can accept depending on the type of map. So what are the bad characteristics distortion-wise in a web Mercator? Well, look at this. This is a web Mercator map. That's Italy, that's Greenland. What if we moved Italy where Greenland is? That's how big it would be. It would be so much larger. We wouldn't like the climate at all, but it would be so much larger. So that's the main problem. Anything that's close to the equator is represented more or less at its sides. Whatever is close to the poles at high latitude looks a lot bigger than it is. And this is a big problem if your act of interpreting the map involves comparing land masses, because you don't know anymore what is bigger and what is smaller. There are types of maps that deal with exact that problem, equal area maps, in which the projection between the sphere, the ellipsoid, and the flat map, the flat paper, ensures that the area is preserved, not the shape. You cannot preserve both area and shape at the same time. That's one limitation of map projections. But in these two maps, Lambert azimuthal equal area and mole weight, the land masses are correctly preserved. So if your map interpretation requires to compare land masses, which your eyes and brain are designed to do, and very quickly, and that's one of the problems, you cannot turn it off when you look at the map, then an equal area projection is the better option. And there are a lot of statistical maps, like FAO, for example. Any large organization, FAO, World Bank, NATO, whatever, deals with worldwide maps in which often the important element is comparing areas by your naked eye, by looking at the map. So that's why, for example, FAO in this map chose the mole weight projection. Let's say instead of area, you are more concerned with distances. That map, believe it or not, they are lines of equal distance at 300 kilometers and 3,000 kilometers and 2,000 kilometers from a city in Slovenia. Equal distance. Can you see the shape? That's not a circle. It should be, but it's not. Because in web Mercator, the deformation towards north takes over and bends the shape so much. You know, if you look at it on the bottom side, you can see a hint of a circle, but then it goes away when you move north. So if you are mapping something and the right perception of relative distances in the map is important for a proper interpretation of the map, web Mercator is a disaster. There are equidistant maps available. That's one example. Yeah, azimuthal equidistant, which you might have seen in some symbols somewhere. And that kind of map ensures that given a point, all distances measured from that point, from the center of the map, are equal. So if the distance is the same on the map, it's the same in reality. Another example is a map that I pulled from the Canadian Weather Service. They have prepared a map projection centered in each weather station. So they have many weather stations, they have many views of that map. And that helps in looking at the map in such a way that you can quickly evaluate the distance between the weather station and the whatever else you are looking at on the map, the cities or whatnot. Again, I'm not saying that you cannot measure the distances. You can totally measure the distances. You can totally measure the areas. You have got tools in WebGIS that you can, point and click, draw a shape, and let it tell you how long it is or what's the area of the polygon that you drew, and it's going to be correct. The problem is when you're relying on naked eye perception of distances and area. That you cannot fix. You cannot shut down your eyes because you're not looking at the map anymore, if you do. Another major sin of the web Mercator projection is that the poles are not on the map. And you might say, well, who cares about the poles? Seals and polar bears, maybe? Actually, as a matter of fact, we do, and we do more and more every day because of climate studies, and the poles are a very important spot when it comes to climate studies. For that, there is projections like the polar stereographic that is designed to look with precision at the two polar caps. And this is an example of a map made by the British Antarctic Survey with GeoServer. Another project is PolarView, which is also using GeoServer on the backend to display map of Antarctica. And, well, no, this is the North Pole, but okay. And another example from the FAO viewer, which is an application that they use internally to look at, I think this is the fisheries department. Yes, it is. And it represents the distribution of types of tunas. Did you know that tunas are disappearing from the face of Earth because we are eating too many of them? They are concerned with this particular problem. And one of the projections that they wanted to look the map at is polar stereographic. So, there are other interesting projections besides Web Mercator. How do we handle all these projections? Well, it should be simple, no? A map projection is just a math formula that, given a point in, let's say, geographic coordinates, turns it into a point in, normally meters or feet, in the space of coordinates of that particular projection. So, okay, I have my coordinates, I take them one by one, I reproject them, and it's all, okay. And it's all fine, no? Well, not quite. Okay, what could go wrong? Something like this could go wrong. That's a map of the entire world, and if I take it and reproject it to UTM-32 North, as is, projecting point by point without taking any measure, that's the result. The monkey is not impressed. What's going on? Well, there's a problem here because we have we are dealing with a global data set, and the projection that I just mentioned is valid in a small area. It's a local projection. There are problems with crossing the date lines, dealing with the poles. All of these problems would require you to prepare the data, cut it, densify it, whatever. Do we have to make all this effort just to display in a particular projection? I'm tired just by talking about it. And then there are autocodes. In the WMS specification, there are some automatic projections that you can use. And you say, oh, I want to use transverse Mercator or equirectangular or whatever, and then you specify the central meridian or the center point or whatever of the projection on the fly, which means it's not totally predictable what projections people will use, because these are projection generators. They generate an infinite number of them. So there's only one reasonable way to do it: automate the preparation and do it on the fly, if possible. That's what the advanced projection handling in GeoServer does. It's a set of heuristics that handle certain classes of projections, not all of them, taking into account a number of problems that might be involved. Let me show you what happens when we activate advanced projection handling. The first step is determining what data we need to read in order to display the map. It's not trivial because, for example, if I'm at the dateline, am I requesting the yellow area, I actually need to read two areas from the source, which are at the antipodes, right? So the area requested and in dashed line, the area that I actually need to read to display the map. And then I have to bring them together into a continuous map. Step 2, cut excess data. We know that certain projections only work at a certain distance from their center or central meridian or whatever. Anything that goes beyond has to be cut before we try to the reprojection, or we are going to scare the monkey again. Then we have to wrap the data. We read it, and we have to wrap it so that we can get a continuous map like this one. So map that gets rendered is in yellow, but the data that we read is the one in the other rectangle. Finally, after doing that, there might still be some data that crossed the dateline during reprojection, and that can generate these long lines. Like I have a little rectangle that is sitting across the dateline. I do a reprojection, boom, it becomes a word-spanning rectangle. So we have to determine where the dateline was crossed by mistake and unfold that crossing. Okay, let's see what happens in practice with this dataset, this global dataset that I had. I'm going to show you two maps, one without advanced projection handling, just dumb point-by-point reprojection, and the other one that comes out of the APH instead. The first one is the reprojection to PDC Mercator. PDC Mercator is a Mercator map, but it's centered in the Pacific. It's centered on 150 degrees in particular, so it's not the dateline, but close to it. If I just do the dump thing, Antarctica goes away because of math projection. It just goes boom, and well, the renderer is tolerant to a certain amount of errors and just ignores them. And well, the Greenland became a world-spanning thing with that's covering most of the northern area. And plus, I don't have anything on the sides. If I activate advanced projection handling, voila, I have everything that I wanted without any particular issue. Greenland is there, it hasn't been expanded, it has been duplicated so that I have the continuous map. Lambert conformal conic. Lambert conformal conic has a cut, a jump in that higher area. And if I just do dumb point-by-point reprojection, I get that absurd polygons at the top. If I use APH instead, stuff gets cut in the area of validity of the projection. Yeah, it's open. Not all map projections are continuous. There's one projection which is called the butterfly, which you should see it. It's made of many separate polygons. This is another case in which I'm just doing a datum change. A datum change which means that both maps are in geographic coordinates, but one is using one ellipsoid, the other is using another ellipsoid. The problem is that moving the ellipsoid moves certain points like 100 meters or a few kilometers away from the original position, making them sometimes cross the dateline. And boom, I got all these weird horizontal lines going around the map. With APH, we detect a dateline crossing, fix it, and we get a continuous map. And of course, we stop scaring the monkey. That was the original result, and this is the cut result, which, well, takes all the geometry and cuts them at 45 degrees away from the central meridian. And you get a nice looking map. Also, map wrapping. Let's say that I'm not doing any reprojection at all, but if I just render the data as is, I get, and I focus on the Pacific, I only get half of the map. I need a machinery that duplicates the map so that I get continuity, and APH does that too. There are other things that are annoying. For example, we get data which is in geographic coordinates, but it is not expressed between minus 180 and 180. No, some scientists decided to make it between 0 and 360 because it makes the math of their model easier. So GeoServer recognizes this case and handles it properly instead of going boom because there are coordinates which make no sense. Satellites, well, Sentinel, Landsat, and so on, they keep on scanning the entire planet. They have this really nasty habit of taking a snapshot across the dateline. Part of the photo is on one side of the dateline, and the other part of the photo is on the other side of the dateline. And I mean, the problem is that Earth is continuous there. It's our representation of it which isn't, right? So they use local projections to deliver the data. All Sentinel data is in some UTM projection. The one at the dateline are represented in UTM-60 or UTM-1, whatever contains most of the image. And, well, they go outside of the projection definition area for the rest. Making a seamless mosaic out of that has been a nightmare. That's kept me pulling hairs for 1 or 2 weeks, but it's there. It's working now. And, well, more projections, because, as I said, satellites provider are giving us data in UTM projections, which means we are getting all 60 UTM zones plus times 2, because we have the north and the south UTM zones, plus the 2 polar caps in UPS. So there's this need of making up a seamless mosaic on the fly from these hundreds of source projection. That's also dealt with in GeoServer. So what are we missing today in terms of APH? Well, one thing that has been my pet peeve for a while, but I cannot find time to implement, is dynamic densification. When you are reprojecting, straight lines, especially if they are very long, should become curves. Like, think about reprojecting a meridian or a parallel in whatever projection you want, it should bend. The problem is that the line is represented by only 2 points. So if we are reprojecting point by point, a straight line becomes a straight line, right? So one thing that you have to do today, if you're dealing with that problem, is pre-densify the data. Add extra points on the straight line so that when they are reprojected, they turn into something curvy. It would be really nice if GeoServer could do it automatically. And we sort of have the machinery in there already. It's just not applied to vector data. So that's one thing that I would really love to do. So in summary, in GeoServer, we are implementing support for more and more projections. So it's not really true that everybody's going 3857, which is a good thing. User dealing with global data typically have to support a multiple projection depending on the type of view they wanted to provide. So, well, they cannot prepare the data for every possible input projection, so GeoServer has to do it on the fly. But things are progressing pretty nicely. If I just can find the time to implement automatic densification, then I'm gonna be happy. So, in conclusion, besides the question, if you have global data sets and you need to reproject them on the fly to whatever projection, give GeoServer a try. You might be surprised. Thank you. Any question? We never did.
Oh, we never did? Okay.
So they are gonna do what we do. In the GeoTools reprojection subsystem uses the information from the original PSG database, which for certain couple of projections give you a formula, straight math going from one to the other without pivoting through WGS84. So for those, we always use that direct formula. When it's not available, then we have to pivot.